Hello and welcome to topic 3, Cauchy-Riemann equations and analyticity. In this topic, we're going to be looking at complex differentiation. We will see that the simple requirement of the existence of a complex derivative imposes strong conditions on a complex function. This will then lead us to define analytic functions, and these have other interesting properties that we will explore in later topics. In this first video, we're going to look at how complex functions can be written as the complex sum of real multivariable functions. After watching this video, you should be able to define partial derivatives of real multivariable functions. You should be able to separate a complex function into its real and imaginary parts. And you should also be able to visualize the action of a complex function. And with that, let's get started.
In the last topic, we looked at real functions of one variable. We're now going to look at multivariable functions. So here we can consider real functions of more than one variable. So we might write this function as f, and it maps a collection of n real numbers to an output, which is also a real number. For n equals 2, so where there are 2 inputs to the argument, we usually label the arguments as x and y. To visualize the action of such a function, we don't just draw it as a graph on the real line, as we do for functions of a single variable. Instead, we draw it over the plane. So we'll have to give ourselves 3 axes this time. This is our x, this is our y, and this is the output of the function f of x and y. So this function is going to look like a surface over the xy plane, so it might look something like this. And what this means is that the height above the xy plane is given by the function value at that point. So we might have that this point here has height given by this position on the function axis, and it corresponds to the output of the function for these values of x and y. The notions of limits and continuity that we covered in the previous topic get generalized, but the main idea is the same. So I'll write that down, that the notions of limits and continuity from topic 2 get generalized. But the main ideas are the same. For what comes next, we're going to need to understand what a partial derivative is. So next we want to look at partial derivatives with respect to the variables x and y, will be useful. These are defined as for normal derivatives by a limit. For example, the partial derivative of f with respect to x we denote like this. Some other shorthand you can use is this curly d subscript x or f subscript x. And we define this partial derivative as the limit, as delta x tends to 0, of the function, so this is the function of two variables, the function evaluated at x plus delta x, y, minus the function value at x and y, divided by the change in the first argument, in other words, delta x. Similarly, we have that the partial derivative of f with respect to y is given by the limit as delta y tends to 0 of the function evaluated at x and y plus delta y minus the function evaluated at f of x and y divided by the change in that second argument, delta y. And from looking at these two expressions, we can see that the partial derivative simply treats the function f of x and y as a single variable function by fixing the other independent variable. So I'll write that down. So these simply treat f of x, y as a single variable function by fixing the other independent variable. So for example, in this second expression for the partial derivative with respect to y, the argument x is unchanged in the numerator, and so is effectively redundant, and we can think of the numerator as being a function of y only. Having looked at real multivariable functions, we're now going to turn to complex functions of a single complex variable. By analogy with the real case that we saw in the previous topic, a complex function of a single complex variable performs the mapping. So the function f maps some input complex number to some output complex number. In other words, this maps the complex plane to the complex plane. The input is a complex number, and we typically, as in the first topic, we typically denote this as z is x plus iy. And we can also write this in modulus argument form as r e to the I theta, where here x, y, r, and theta are all real numbers. The output of our complex function is also a complex number. So the function, which takes z as its argument, returns a number, and we separate that into real and imaginary parts as u plus I times v. And again, we can write this in modulus argument form, where we use capital letters to distinguish from the input. And in this case, also u, v, r, and theta are real, and in fact they are real functions. Real functions of the complex inputs. And I'll write this below to emphasize that u and v are functions. So the function u maps some complex input to some real output, and similarly for v. U, which is the real part of the value returned by our function, is itself a function that takes a complex input and returns a real output, similarly for v. We have that the input to our function z equals x plus iy. So it's easy to see that since z is completely determined, by the real numbers x and y, we can actually view this, this function of a complex variable as a complex function of two real variables. So we can view f as a complex function of two real variables, because the single complex number z is described by the two real variables x and y. The same also goes for the functions u and v. So the functions u and v, we've seen above, they take complex inputs and yield real outputs. And those complex inputs, again, can be described by two real variables. In other words, we can write our function of the complex number z has a real part, u, which is a function of two real variables, and an imaginary part, v, which is also a function of two real variables. So u is a mapping from two real numbers to one real number, and the same goes for v. I'll quickly write down a couple of examples so you can see how we write down u and v. So let's take the example that f of z is z. In other words, x plus iy. Well, then it's easy to see that the function u is x and the function v is y. If instead we try something like z squared, this is x plus iy squared. And I'll leave you to do this, but if you multiply that out, you find that the real part is x squared minus y squared, and the imaginary part is 2xy. Given this connection, we will see that insights from multivariable real functions will be useful when studying complex functions. The next question we want to consider is, how do we visualize the action of a complex function? Recall that our complex function maps the complex plane to the complex plane. So the domain and range of our function are the set of complex numbers. The domain and range can therefore be drawn individually in 2 dimensions. In other words, our input is the complex plane, where the real part is x, the imaginary part is y. Under our complex function, f, this gets mapped to another complex plane, where now the real part is given by u and the imaginary part by v. Of course, drawing both of these together would require 4 dimensions, and 4-dimensional paper is hard to get hold of. So instead, there are various ways of visualizing the action of the function f. I'll say drawing this mapping requires 4 dimensions. I'll note there are various ways to visualize f. There are various ways to visualize f. So one way is to use color for phase and height for modulus, real, imaginary. What I mean by this is that you give yourselves a set of xy axes to describe the input to your function, and then the height above the xy plane determines the modulus, or the real part or the imaginary part of the output of your function, and the color that you assign to that point describes the phase or the argument of the complex number you get as the output. I'll point out that on the additional content on the Blackboard page for this week, you'll be able to find some code that allows you to plot functions in exactly this way. And I encourage you to play around with this because it's very useful to be able to visualize what's going on for some features of complex functions that we'll encounter later in the course. There are a couple of other ways that you can visualize the action of a function. You could also draw sets of curves in the xy plane and see where they get mapped to under the function. We call those their images. So you'd have 2 sets of curves on a single set of axes, one describing xy inputs and the other describing uv outputs. Lastly, you could also consider drawing 3D plots for the multivariable functions u and v, as we did at the beginning of this set of notes. In topic 2, we looked at notions like limits and continuity. And so notions such as limits and continuity, these are the same for complex functions. An important difference, though, is that now, instead of reasoning about intervals on the real number line, so you'll recall that we had things like the absolute value of x minus x naught less than delta meant something like, so we had the real number line, and we had x naught, and then x naught plus delta. So given this expression, this would be the valid range of x values. So instead of reasoning about intervals on the real line, we now reason about disks in the complex plane. And I'll draw a picture to show what's going on. So we give ourselves a real and imaginary axis, real, imaginary, and we might have some point of interest, z0, and if we now say that we're interested in points z that are distance delta from the point z0, this now defines a neighborhood about Z0. And this looks like a disk in the complex plane. That's meant to be centered, where this radius is delta. And I'll note that in problem sheet 1, you showed that this expression, the modulus of z minus z0 less than delta, defines a circle in the complex plane. That's the end of this first video of topic 3. As a quick recap, we looked at multivariable functions and the definition of partial derivatives. We then looked at complex functions of a single complex variable. We saw that such functions can be reinterpreted as a complex function of two real variables, u and v, and we considered a few different ways of depicting the action of a complex function. Next up is the second video of topic 3. Thanks for listening.